أهلا وسهلا مرة ثانية. Welcome back. Today is day 2. We are in the Six Sigma Green Belt, and yesterday we were in the measure phase. We're still in the measure phase, and yesterday we decided what sort of data we need to collect, the sampling rate, the frequency, and so on. And before we move on, it's very important that you do measurement system analysis. And what is measurement system analysis? Is just you're trying to get to the source of variation. If you have an error, because garbage in, if you use wrong data, then basically garbage in is garbage out. So it's very important. It's very important that the data that you use is good data. And the measurement system error is basically you want to know where is the source of your measurement variation. Of course, when you get the data will not be the same, and there are sources of variation. Let's say you're measuring the height of a Pepsi can or whatever, or anything. I don't know, the weight of a potato. You know, so there are variation. They are different. So the sources of variation, they come from two ways, basically. Either the variation of the part itself, because each part are different. If we take our weights, of course, my weight is different than your weight. His weight is different than the other person weight, and so on. So there is a difference coming from the part itself. They call it part-to-part variation or variability. But there is also a variability that is coming from the measurement system itself. And the measurement system here, as you look at it here, so we have the overall variability. Part of it is part-to-part variability, which is fine. This is what we want to measure anyway. But there is a measurement system variability, and this measurement system variability comes from two things. From something called repeatability and another thing called reproducibility. And they're very simple concepts. Repeatability, and this is why they call them gauge R and R, you know, repeatability and reproducibility. Repeatability comes from variation due to the gauge that you're using. If it's a ruler, maybe it's a variation of the ruler itself, okay? If it's a scale, maybe it's the variation of the weighing scale. Whatever you're using, if it's a thermometer, maybe it's a problem with the thermometer itself. So this is due to the gauge. So some variability is coming from the gauge, but another variability is coming from the operator, the appraiser, the one who is actually taking the measurement. If I take it, maybe it's different than if you take it. Maybe you're more skilled in taking the measurement than I am. So part of this measurement or this variability is coming from the gauge itself, and another variability is coming from the appraiser, the person who's actually doing the measurement. And for the operator or the appraiser, there is an operator in himself, and there is an operator by part. Maybe one part is good in measuring, maybe another part is not good in measuring. So that's basically what gauge R and R is, and what system measurement is, measurement system analysis is. So here, if you look at this equation here, we have the overall variability or variance here is coming from the part to part, which is this part, the repeatability part, and the reproducibility part, which is operator and operator by part variability. So we have basically these sources of system variability. And unless you make sure that your measurement system is a good system, then whatever data you feed into the analysis, when you go to the analyze phase, is basically garbage in, garbage out. This is why you want to understand this concept first. So, and after you understand the concept, all you need is just take the data, plug them into a software, and the software will do the rest for you. It will tell you how much part-to-part variability, how much repeatability, how much reproducibility. But understanding this will tell you where to look for when you have measurement system problems, basically. Why is it not moving down? All right. So we have repeatability and we have reproducibility. So what is repeatability? Again, as we said, very simple. It's variation in measuring equipment. It's a variation in the gauge. So that's what repeatability is. And I'm having a problem, I guess, with my cursor here. And reproducibility is due to human inability to reproduce the same measurement, basically. So one is for the equipment and one for and gauge R&R, which is repeatability and reproducibility, is a measure of precision by taking one part. You take one part basically, and you measure it several times with different people to see. Is there a problem with the measurement system? Is there a problem with the repeatability? Is there a problem with reproducibility? It's not an absolute value, it's a relative value. And it's just like if you're going to measure a distance between here and Riyadh, it's different than if you're going to measure the distance of a book. That one is in kilometers, this one is in centimeters maybe. So you're going to use different things. So the customer tolerance itself is relative. The measuring the distance from here to Riyadh is not going to ask you by the centimeter or by even the meter and so on. The scale will be different than measuring this. This is Minitab. If you just take the data and just take, you take 2 pieces or 10 pieces of equipment, for example, and you measure them. You have 2 or 3 people measuring the data, and you just put them like you put the data in Excel sheets and columns, appraiser 1, appraiser 2, part 1, part 2, and so on. And you just put the data. It will analyze this data for you, and it will give you a chart like this one. And the way to read it is not very difficult. Here, this one is the part-to-part variability, meaning the parts themselves are different, just like our height or our weights. So there is a variability coming from the variability of the products themselves, of the parts. My weight is different than your weight. It's actually different, okay? But there is gauge R&R contribution, which is this level here, and this is a breakdown of the gauge R&R. So this is repeatability, and this is reproducibility. This one is just a control chart for detecting the special causes and so on. So it will tell you which way, which data point is not likely to be within the data and so on, like an outlier. And this side here, you have you look at the data. This is by part here. So you can see that this part, which is part number 10, if you're taking 10 parts and you're doing measurement, and then you're asking different people to measure them, this is basically, you can see that part number 10 is the most difficult to measure. Why? Because you can see that there is a big variation here between the different measurement, basically. Here, this box of block, we will talk about it later. As you can see that this one here, appraiser number 2, has the lowest reading among all. So you want to watch out. This guy has the lowest reading. Is he the right? Is the right one, the wrong one, and so on? And this bottom one is the same as this top one. It's just by appraiser. So all the information is there, and just it helps you if you have variability, where this variability coming from, because Six Sigma is all about reducing variability, okay? But you want to see where the source of variability or variation is coming from, so you can actually, if it's from the part, then you want to focus on the part. But if the problem is coming from the measurement system, it's just the way they're measuring. It doesn't really have high temperature, it's just whoever measured him is actually either he has a bad instrument or he's not a good appraiser. If we look at this is gauge R&R ANOVA. ANOVA means analysis of variance. And you probably see questions like this in the Greenbelt exam. So in gauge R&R, you use ANOVA. ANOVA is analysis of variance. And do you remember what variance is? Variance is basically the square of the standard deviation, if you remember the statistics that we did. So it's basically you're actually collecting the variance, and you look at it like this. You see that most of the contribution of the variance is coming from what? From part to part. Hi, Muwaffaq. It's coming from part to part. So it's like almost 90%, which is okay, which is fine. This is where you want most of your variability to be coming from. You see that repeatability or gauge R&R is 11%. Part of this R&R, there is the 2.5% coming from repeatability and 8.6% coming from reproducibility. And within this reproducibility, the 1.9 is coming from the appraiser and 6.66 is coming from the appraiser part. So this is just a way to measure your data, to see if you have good data, do you not have good data. It's very important when you move on. Again, all of these concepts, until you actually go and take a project and take data, then it will make good sense. It's just taking different data. And normally in face-to-face classes, we bring real things, let's say even if we bring potatoes, 10 pieces of potatoes, and we ask 10 people to measure, or let's say 2 maybe or 3 people to measure it, we take the data and we see that some of the variability is coming from the difference in the potato itself, some of it is coming from the gauge, which is the scale, some of it is coming from the people, but this is what gauge R&R. And in statistics in general, your gauge is the p-value. If the p-value is low, that means things are going very well. So here, for example, you see that it's 0.05. So appraiser basically has effect, and also part and appraiser also, has an effect. Well, basically they all has an effect. All right. We've seen this. Now, before you move on, this is a measurement system. A drill down is basically a structured approach to check the data quality. You want to check the data that you collected. You want to check the quality of it. Basically, the drill down, it is to find the source of the component. You want to challenge each component for possible errors, either it's bias or precision, and then decide if the source is acceptable. You just move on and you go on to the next. If not, then you document your decision and you move forward. So that's about gauge R&R. Another important thing in the measure phase is the first pass analysis. And the first pass analysis should be done actually and should be completed for each KPI. You decided in what KPI you want to use to measure your performance. So you want to do first pass analysis on the data that you took. You took the data, you want to measure your current base performance, take the data and run first pass analysis. And all of these, as I told you, once you are familiar with the software like Minitab or Sigma XL, then all you need is just take the data and ask the software to produce something like this for you. Here, the dash line is basically indicate the baseline. And let's look at this. First pass. What can you read from this? This is basically time. The x-axis is time, and this is the data. So this is you're measuring the data with time. What do you see here? Anybody? I can see trend. I can see an upward trend. The data actually with time is going up. So this is a piece of information. Before I move on even to the analysis, I'm still in the measure phase. And I also see a repeating pattern. So goes up, goes down, goes up again, goes down, goes up, goes. So there's something that I can tell from this information. So before I move on, I need to understand what is the problem or what is going on. Maybe it's not a problem, but what is going on with the collected data before I can actually just make a decision, take their average or do whatever, you know. I need to see what's going on. What do you see in this? Can anybody try to make a guess? What do you see about this data? Anybody would like to give to take a go on this? Well, what I can see a significant step in the past. So the data was going like this, and then there is a significant steps that going up. And then you can see that there is probably a downward trend. So all of this will give you clues. You know, you took the data, you want to know. Again, you can't improve without measure. You know, you can't without, if you can't measure it, you can't improve it. As simple as this. So this is all good. You're taking data, you decided how you're going to measure your problem. You're plotting the data, and you're looking at the data, and you are examining the data. So process stability. Process is stable if it's in control and predictable. And all causes basically are called common causes. Or the process is unstable if it's not in control, and there some special causes exist. Basically, that's what the process stability is. So now, is this process stable? Anybody? I see it's stable. It's nothing. Yes, there is variation, but variation doesn't mean necessarily that's not stable. Okay. How about this one here? Is this process stable?
Not too much. There is some spikes.
Yes, absolutely. There are 2 points. It's pretty much stable, except for these 2 points. So it's appear to be stable, but the exception is there are probably 2 outliers. So now, what you want to do, you want to see these data points. Why are they like this? Is they real data, or are they just an outlier, meaning that they are not correct data? Or just a special cause? You know, somebody's norm is to come at 7 o'clock in the morning, but today he came at 9 o'clock. What is it wrong measurement, or is it a real special cause? It just maybe has an emergency or something. So you want to deal with this data differently, separately. You don't want to include it in your data. You want to say this is an outlier. I'm going to take it out. I'm going to first of all find out the special cause. What happened there? What is, and is it going to happen again or not? But I don't want to make it part of the whole analysis. How about this one here? Give it a try. Again, this is just like we said before. This is
there's a step.
It's not stable with time. Change should be investigated because there is a significant step upward here, and there is a downward trend. So maybe it's not. So that's basically about stability. Again, all of these tools, they're not very difficult. Once you understand the concept of them, all you need is just take the data. Normally, you put them in a software, you produce these graphs, you look at the graphs, you look at the analysis that the software will give you, and based on this, you make a decision. Because if you don't look at the data carefully, if you don't examine your measurement system carefully, you can be making big wrong decisions down the road. You think that you have a problem when you don't have a problem, or maybe it's the other way. You don't think there is a problem when when there is a problem. So you want, first of all, say, okay, we took data. Let's look at the data, and here are some tools to look at the data to make sure that our data is good, to make sure that our measurement system analysis is good. We know where the sources of variation is coming from before we move on into the analysis of the problem. Now, one important thing is the process capability.
Thinking that something wrong with my network connection, but
was there something wrong with me?
Me too.
Can you hear me?
yes.
Yeah,
Yes, we
doctor. We
can.
lost you for like 2 minutes.
Oh, okay. Maybe it was my connection. Okay. Let me see. Am I there still?
Yes.
Yes, we can hear you. I see you.
All right.
The slides are not showing.
The slides are not showing?
No.
Let's see what I can do. How about now?
Yes, it's shown now.
It's showing now, but it's not in slide mode, right?
Yes.
I'm trying to. Okay, is this fine? Can you see it? Okay.
Yeah, it's clear.
Okay. I don't know why I cannot put it in a slideshow mode, but I'm not sure about that. I don't know if I actually did the recording or not for this. I'm not sure, but maybe I'll check it later. Anyway, after you decided what data you want to collect, and you checked if there was any error in it, you checked the stability of it, and so on and so forth. Now what you want to do, you want to establish your baseline performance. What is my performance now? And this is called process capability analysis. And process capability is a measure of how satisfactory the process in relation of the customer of the process. Basically, how are we doing in comparison to what our customer is requirement? It's like we said before. It's the process, the voice of the process against the voice of the customer. So there is something wrong here, but I don't know. It's just like hang up a little bit. But anyway. So overall capability is a relative measure of a spec limit to control limit. Now let's look at this. Let's say that our red lines are our specification limits. Let's say that our customer wants us to be, he doesn't want anything more than this value, which is the upper specification limit. And he doesn't want anything to be lower than this value, which is the lower specification limit. And let's say that this is our process here. Do you think that this process is capable? Please,
Yes, it's good.
even if it's the wrong answer, it's fine.
Should be capable, yes, I think.
It is capable because most of my data are actually within the upper specification limit and the lower specification limit. But how about this one here? Is this capable?
No, it's definitely not.
It's not capable. Why? Yeah, why? Because my data are actually crossing the line of my customer. The customer wants it between, let's say, 2 days and 5 days. And now some of my items are arriving more than 5 days, and some of the items are arriving below 5 days. So this process is not capable. How about this one here? What do you think? It's capable from one side, but it's not capable from the other side, right? So it looks like capable, it will not touch my upper specification limit, but it is touching my lower specification limit. So my capability has to be, my data has to be within the lower specification limit and the upper specification limit. How about this one here?
It is.
Capable.
It is capable. It's within.
It's capable from one side, but it's not capable from the other side. So that's the, you know, so I'm very sure that it will not touch the lower specification limit. If my customer say, I don't want anything below this value, I don't think anything is going to go below this value. But if he says that I don't want it either to be above this value, then I can't guarantee because it doesn't look too good. Yes, most of the data are here, but it's still not capable because the likelihood of it touching the, you know, although there are, most of the data are actually within the upper specification limit, but it's not capable. Why? Because it's very likely that one point will actually go. It's just like somebody is nearly touching the wall. So I can't guarantee that he will not actually cross the border. So that's what capability is. So how do we measure the overall capability? The overall capability is very easy to measure. And again, everything will be in a software. We just need to understand the concept. There is the PP upper, which is basically this distance divided by this distance here. See this distance here, this is one distance here from the mean to the upper control limit, which is a 3 standard deviation always, or 3 standard of the mean. So it's always a 3 standard deviation. This is how we set our control limit. So the PP upper is basically this distance from here to here, divided by this distance from here to here. And since this distance is always a 3 standard deviation, so in the formula it will always be the standard deviation. So that's what the PP upper. The PP lower is the same concept. It's actually the same thing. It's this distance from here to here divided by 3 standard deviation, which is the lower control limit, or the mean minus the lower control limit, which is 3 standard deviation. The PP, which is not the PP upper, not the PP lower, is just the whole thing. The overall is basically the distance between the 2 red lines divided over the distance between the 2 black lines. And what's the distance between the 2 black lines? It's 3 plus 3, so that's 6 standard deviation. So to measure your overall capability, it's basically the upper specification limit minus the lower specification limit divided by this distance here, which is 6 sigma. Is this clear? Let's take an example. Maybe with an example we can see it a little bit better. Let's say I'm collecting the oil level in a tank. And let's say I calculated the average to be 75 centimeter with a standard deviation of 10 centimeter, as we did yesterday. This is how we, it's easy now to calculate the average and the standard deviation. And let's say the maximum and the minimum allowable limits, which is, this is my customer specification now, is saying I don't want it to go below 60 centimeters because that's going to create problems for me. And I don't want it to go above 100 centimeters, okay? So what is the PP upper? The PP upper is very simple. We take the upper specification limit, which is the 100, this is the upper specification, the upper value that our customer wants, minus my average, which is 75, divided by 3 standard deviation. So we get 100 minus 75, that's 25, divided by 30, so I get 0.83. And anything below 1 is not really good. That's a rule. You need to have it at least 1.5 and even more, you know, 2 will be perfect. That's 6 sigma. But you don't want this to be below 1. Now, how about the PP lower? The PP lower, basically, it's going to be, again, the distance, but now between the mean and my lower specification limit. So it's 75 minus 60, and that's 15, again, divided by 3 standard deviation, which is 30, and we're getting 0.5 here, because it's 15 divided by 30, and that's 0.5. So that's the PP lower. The PP, the overall, it's basically the distance between the upper specification limit minus the lower specification limit, which is 100 minus 40, divided by the distance between the control limits, which is 6 sigma or 6 standard deviation. So that's basically 40 divided by 60, which is 0.66. And all of these are, the PPK is actually the minimum of these two. That's the minimum of these two. You just be more conservative, and I say, well, I don't think my performance is good, so I'm going to take the lowest of the two. Just being conservative. So that's what PPK is. So that's basically how you calculate process capability. It's very simple, but it gives you a lot of information. It tells you that is your system capable? Does it need improvement to start with, or does it need improvement? If you're doing very well, if your PP and PPK and PP upper and so on are good, then you probably say, why do I even, you know, worry myself and try to work in this project? Because it's cost money to work in project, you know. At least it will cost you your time. So this is a good tool. Once you decided what data you want to measure from the beginning, this is the beginning of the measure phase, you made sure that this is exactly what you want. You took the data that you want. You made sure that there were no errors, no repeatability, reproducibility problem, no stability problem, and so on. So you're happy with the data. Now you look at the process capability of your data. You look at the process capability of the data, and then you decide, am I capable of meeting my customer's requirement, or am I not capable of meeting my customer requirement? So this is a good tool, and probably sometimes you could probably stop here and say, well, I think at least now we have a peace of mind that this process is doing very well. Or if you have a problem, then you continue to the analyze and improve and control phase and so on.
Doctor, excuse me.
Yes?
I have a little confusion, because before we were talking about the data analysis, right? And now this indicator can give us an indication about the whole project. Is it going well or not, or about the data analysis only?
Actually, from the start of process capability, now we are gauging our performance. Before process capability, we're looking at what data do we want to collect, and then whether this data is good or not. This is why we did gauge R&R. Before we move on, we want to see, is the data that we have are good data or not good data? And then we looked at the stability of the data. But once we started the process capability, now we are confident, we passed that stage. We're now confident that our data is good. Now we're measuring our performance based on the KPI that we decided that they are good for us to measure ourselves in. So based on this, I'm doing process capability. Now I want to measure basically my ability to meet customer requirement. So to answer your question, before process capability, yes, we are examining the quality of the data. But once we start the process capability, now we are sure that the data quality is good. And now we're starting analyzing how we are doing in terms of meeting the customer requirement. Is it clear?
Yeah, very good. Thank you very much.
Good, good, good. Excellent.
Sorry, doctor, I have a question.
Yes, please. Is this Hawra?
Yes.
Hi, Hawra.
Hi. That means from the process capability, we means now we will move on for solution for our problem from this step.
Actually, yes. This is the process capability. Basically, is the end basically of the measure phase. Although we're going to take about a few slides, you know, at different metrics. But basically, yes. Once you do process capability and you see how capable. And if you're capable, then that's it. You need to document and then maybe do some control and so on. But process capability is this tells you where you are now. How are you performing at this point?
Yes. Can we move on for the next step or not? That means this is the process capability, right?
Yes, you're done with the process capability. Normally, you would go to the analyze phase now.
Thank you.
If you have a problem. If your process capability tells you that you're fine, then maybe you don't need to move on. Close your project, go to your management, say congratulations. We looked at the data, we're very capable, we're happy with our performance. We're going maybe to go to the control phase to make sure that our performance, we will sustain our performance, but we're not going to do any further analyze or further improvement or so on. Once you are happy with your performance, then I don't see there is a point for improvement. Unless you really want to be something, you know, maybe your competitors are doing much better than you, then it's another story. Just this is, you know, you want to gauge yourself against your customer specification and maybe against your competitors as well. Is that clear?
Yes, thank you.
So could we say that till process capability, it's define, measure, analyze. So beyond this would be the improve. Would that be correct to say that?
No. We're still in the measure phase. We're just
okay,
measuring.
Because you're analyzing this these graphs.
Now, actually now, I'm still just measuring my performance now. I'm not analyzing. Well, I am analyzing the data that I'm measuring, but this is only analysis of the data itself. Okay. Now I haven't decided whether I need to analyze phase is analyzing the problems, not analyzing just the data, the quality of the data, and the performance and so on. The analyze phase is once you decide that you do have a problem based on the data, which is the measure phase, you go on to the analyze phase to see where your root causes are. What, you know, why are you not performing very well? But before you go into analyzing why you are not performing very well, you need to establish that you are not performing very well in the measure phase.
Okay. So this is still a part of like defining the extent of your problem, or saying whether you have a problem or not.
Yes, but it's in the measure phase. Yes.
Okay.
Yes.
Thank you very much.
Yes. This is an exercise. If you want to go back tonight maybe and try to calculate the PP lower, PP upper, and so on, PPK. All you need is just to measure the mean, the standard deviation, and plug into the formula. As simple as this. Your specification limit is 2 mil. So that's what you want. And of course, your lower specification limit will be 0 because. And you can, this is a cheat sheet. You can see if your solution is right or not. Now, actually some slide I just added because I know that they will be mentioned in the green belt, but there is the PPK and the CPK. And the PPK is for long term, while CPK is for short term. Because there are long term variation, you know, over the whole process, and there is a short-term variation that has to do about a certain period and so on and so forth. So the PPK is for long-term, the CPK is for short-term, and long-term variation contains all forms of variation in the process, while CPK indicates whether the process can actually potentially meet your specification. It's a good measure, because as we say sometimes, if you were able to do it once, why can't you do it many times? Yes, overall you're not doing very well, but there are pieces and chunks in your process where it says that you can actually potentially meet your process. So this is what CPK is. And basically, if there is a big difference between the two, if you see that your CPK and PPK are too big of a difference, very big, then it can also be an indication that your process is not in control, it's out of control, and maybe. But the calculation is the same as we've seen now. Okay, but normally what happens here, you go to a software like Minitab, and in Minitab it will actually give you all this data. And let's look at this Minitab here. Let me see if I can actually do a slideshow again. Maybe it will work this time. All right, that's better. So here, this is a result. Just you're only taking the data that you measured. Let's say it's time data or height data, or I don't know, overjet maybe data like in dentistry, or overbite data, whatever it is. So you're taking these data and you're basically putting them into the software, like a statistical software like Minitab. So it will give you, and you're given it the data, you're given it some data also. You're given it your lower specification limit. That's the minimum you want your data to be in. And you're given it your upper specification limit. That's what USL means. And this is the sample mean. The software will calculate it for you. We'll just take it and basically will calculate the average. And this is the sample size, which is N. It's taking 100 points. Let's say you took 100 points and you plug them into the software. That's your standard deviation, the overall, which is basically the long term, and this is the standard deviation within, this is the short term here. That's the difference between the CP and the PP that we said. And here, this is your overall capability. You have the PP, you have the PP lower, you have the PP upper. It will calculate it for you. You have the PPK, which is the minimum of the two, and you have the CP also, CP lower, CP upper, and CPK, and this is your performance here. That's your performance. So the part per million that are less than the lower specification limit, you don't want to be lower than your lower specification limit. Basically, the observed, you have nothing. None of them actually went below your lower specification limit. But let me ask you this question. Let's say you took 100 data points and you found that these data points, they're all above your lower specification limit. That means, satisfactory, basically. What is this? Does this give you confidence in the data? Not necessarily, because this is what it's saying. This is saying there is an expected value, although most of them, they did not go below the lower specification limit, but because of the way it is going, the variation, it is expected that you will actually miss in the future. So this is the purpose of the expected here. So you're expecting maybe around 4,000 in a million misses, in your whole process. So that's the expected overall, and that's the expected within. This is the same for the upper specification limit. How many times you have actually been outside your upper specification limit, and this is the total, which is being lower than the lower specification limit or higher than your upper specification limit. But that's, all you need is just look at them, and this is your lower specification limit. This is your upper specification limit. All you need is just take the data, put them in a statistical software like this, learn from this data. You can automatically say that I'm not happy with this performance because all of them are below 1. That's not good at all. So, and this is my performance. This is what I expect to be my performance in the future. This is, I expect that I will have this much error. I will have about 4,000 errors in a million chances. So that's, you know, whether this is acceptable or not acceptable is another, but normally, if you have these below 1, then you're not happy. So basically, you're just taking the data, you're plugging them in the software, and the software will tell you. What we are supposed to be doing as a green belt or as a black belt, you need to understand these concepts, and you need to be able to read these charts as simple as this. And the way you read it is very simple. You put the data and you say, I'm not happy with this process because it's less than 1. And then if somebody asks you what it means, you can explain what it means. So that's the purpose of the thing. The purpose is not to actually bug you with so many formulas and so on. No, the purpose is to tell whether you have a good performance or not. And in everyday, you know, practice, we're collecting data. All you need is just plot this data and see, are you doing well or you're not doing well? But before you do your process capability, as you said, you need to check the data. You need to make sure that you are actually taking good data. You don't want to be measuring somebody's temperature with a bad thermometer and they say, look, I'm not doing very well. This is what we said before, you know, gauge R&R and so on, and measurement system analysis basically. So this is all very important. Let's move on. There are other metrics which are important. If you are going for green belt, or if you're going to be certified as a black belt, this is part of the content. You need to understand it, and they are very important, you know, because most of it, you know, not all of the data are continuous data. Most of the analysis that we did were for continuous data. But as we said, there are continuous data, there are count data, and there are attribute data. So the metrics for other than the continuous data, you probably want to use things like this. And let's start with some definition. And let's start with here, computing a process signal. You need to know what a unit means. If you're producing parts or units, it's basically the item being produced. Whether you're producing coffee, you're producing service, you're producing denture, you're producing a graduate from your technical college, you know, these are all product. Okay, and some of this product will be good product, and some of these products will not be good product. And these not good product in Six Sigma terminology, they're called defect. So if he's not good, then it's a defect. So a defect, what's a defect? A defect is any event that does not meet the specification. A specification of what? The specification of the CTQ. Again, everything is linked together. We establish our CTQ, critical to quality, as defined by the owner, as we spoke with the owner, as we surveyed the owner, as we you know, held a meeting with the customer, not the owner, sorry, with the customer. So based on this, we established our KPI, our specification. Now anything that does not meet this is called a defect. So this is very important. Also, another important definition is the defect opportunity. A defect opportunity is any event which can be measured that to provide a chance of not meeting customer requirement. But let me explain it with this graph here. Let's say your product is an invoice. You have an invoice that you're producing an invoice. So this is an invoice, and there is an opportunity for an error. Let's say maybe you will not put the invoice number right. That's an opportunity for making a mistake. So is there an opportunity for making a mistake? Yes, a threat may be a better word, but in English, opportunity can be negative and it can be positive anyway. Maybe here's another thing, the voice date. That's an opportunity to make a mistake. Maybe whatever, the due date. That's maybe you'll make a mistake here and so on. The bill address, the ship address. So let's say you have in this invoice 10 possibility to make an error. This is called opportunity to make a defect. So how many defect opportunity here in this invoice? We have 10, basically 10 opportunities. Now, let's say we are producing 8 invoices. So how many opportunities there are in 8 invoices? Anybody? Well, we're producing 8 invoices, and in each one there is 10 opportunity to make a mistake.
100.
What?
100.
Is it they're 8 only, they're not 10. So we have 8 invoices times 10 opportunities.
80. Sorry.
80. So that's an 80. So they have 80 opportunities to make mistakes. Now, let's say we have a total, we took data and we have a total of 5 defects in all 8 invoices. We calculated, you know, all the invoices, we only had 5 defects. So what does this mean? We have a defect per unit of 5/8. So we have 5 defects per 8 invoices. So that's called defect per unit. But defect per opportunity, we have basically 80 opportunity of mistakes, but we only made 5. So 5 divided by 80 this time is 0.065. But because this number can sometimes be very small, normally we multiply it by 1,000,000, just like we sometimes multiply by 100%, just to convert the number from a proportion to percentage value. So we multiply this by 1,000,000. So the same number, instead of saying 0.0625, we say 62,500 defect per million opportunity, or DPMO. So this is how you calculate defect per unit. This is how you calculate, normally nobody asks about this, they go directly to this one, but this is how you calculate DPMO, which is defect per million opportunity. And again, the process capability that we did before is normally for continuous data, but if you don't have continuous data, it's not something that you measure in a continuous data world, you're measuring it in an account data world, then you want to measure this. How do we convert this to sigma? It's very easy. There is a table. You just go and you convert the same analysis. You can do it again. Let's take this example. Maybe take a minute. Let's say assume that the product is a television. You're producing television, which contains 800 opportunity for error. In this TV, there is 800 opportunity for each one TV. There is 800 opportunities for error. And the total production is 2,500 units. And the number of defects that we found were only 450 defects. What do? We just use the same thing. You know, we calculate the DPU, the defect per unit, which is 450 divided by 2,500 units. And once we get this, we divide this again by the number of opportunities in each one, and we multiply this by 1,000,000 to get it in a DPMO. Once we calculate this, we calculate the DPMO, which is 225. Now we have 225 DPMO. How do we convert this to sigma? Very easy. You just look it up in this table. So we have 225. Where does 225 fall? Between what sigma and sigma? We have 225. 225 is basically between this value.
5 and 4.
Between
5 and 4.
I think 5 and 6, isn't it?
Yes, 5 and 6.
Yeah, it's 225. Oh yeah, you're right. Between 4 and 5, you're right. So it's there. So I know that my performance is between 4 and 5 sigma. I know that the chances, the yield is basically is the opposite of the DPMO. This is chances of error. This is chances of success basically here. This is what it is. So I'm like 99.38% or 99.9% sure that my product will be fine. That's basically what it is. So that's the way you calculate your DPMO, and that's the way you convert it to a sigma level, and that's the way you calculate it to basically convert it to yield, which is risk here. Now, one last thing in the measure phase before I conclude the measure phase. You might be asked about rolled throughput yield. And basically, it's a very, very, very simple concept. If you have steps in your process, and in each step, there is a probability of success. So let's say I do the first step, and my probability of success is 99%. And then the next step goes to Dr. Fayaz, and he does it. And let's say his success is 99 again, or 99.5. And then we take it to Hawra, for example. Then let's say she's 98. Then what is the rolled throughput? It's basically you multiply these numbers together. So the first one, there's a chance of success of 99 multiplied by the second one, 99.5 multiplies by the third one, 99, 98, whatever. So the total, the product of these numbers is basically called the rolled throughput yield. That's if the process is in series, one after the other. Once it gets in parallel and combinations and so on, then the calculation gets very, very, very sophisticated, and maybe you need special softwares to calculate it. But normally, for a process that is in series, one after the other, you just take the yields, which is this value here, these, and after you calculate them, and you just multiply them together, and you say this is my confidence basically in my process. We're done with the measure phase. We're gonna go to the analyze phase, and it's 8 o'clock. I don't know, I wonder maybe it's time to break for 15 minutes and come back. So